When you're looking at capacitors and alternating current, it's inevitable that this idea of phase relationships comes up. And what it's talking about is and this is kind of linking in a little bit with this final point as well, if this is a graph of voltage against time, on that graph, remember we've got the alternating current, which is like a sine curve. We can look at the voltage across a resistor, AC. We can look at the voltage across a resistor compared to the voltage across the capacitor compared to the voltage of the supply. Each of these being voltmeters measuring them. So if we first of all take the voltage across the resistor, okay, with our blue line here, with our classic sine curve, if we then, remembering if this was DC, the capacitor is a little bit slow to respond, because as the voltage increases in the circuit, which would be the increase corresponds to the increase in voltage across the resistor, the capacitor takes a little bit of time. It lags behind. It'll peak a bit later, so it takes a moment to respond. And what we would notice, and what we do notice, is that the capacitor peaks 90 degrees after the resistor voltage does. So it happens to be just sort of following everything just a little bit behind the 8 ball. Exactly 90 degrees. And that's what we're talking about when we're talking about this phase relationship. The voltage across the capacitor, VC, lags behind by 90 degrees, and it's lagging VR, I should say, by 90 degrees. Now, one point of confusion that always comes up is that we use the two troughs here. It appears that the capacitor is actually ahead ahead of the resistance. Remember, this is VR and this is VC. But remember that this is the time axis, so as time's passing, you can think of this as a constantly growing. As time passes, it hits VR first, and then as time continues to pass, it hits VC. So that's what we mean by VC lagging by 90 degrees. Where does the 90 degrees come from? If you explore this on an oscilloscope, which is like a real-time voltmeter, a normal digital multimeter or a analog meter will give you a DC equivalent, or the analog meter will actually wiggle around, but if it doesn't respond fast enough, it'll give you essentially a DC equivalent. Actually, I think I need to experiment with that. That would be quite a good one to test. I don't know if I know that for sure, or if it's intuitive. In any case, when you're using a digital multimeter, I know this for sure, that gives a DC equivalent, which is dividing the peak by 0.7, by the square root of 2. Okay, so that deal, I think, deals with the phase relationship between the capacitance and the resistance. Now, the trick of it is that the supplier is still having to supply the voltage across each of those, so the supply voltage still equals the voltage across the resistance plus the voltage across the capacitor, and this is at any point in time. Okay, this is at any point in time. However, this is not true for RMS. Okay, not RMS. It doesn't work. This formula does not work for RMS. Root mean square values, dividing by the square root of 2. And that's because the RMS deals with an overall average, whereas this equation deals with the peaks. They're peaking at different times. Okay, so when one is higher than the other one will be lower, but it'll still add to the supply. Now, how does that work on the graph? If we switch to yet another colour, sorry, I don't like using more than 3 colours, but if we add these two together at any point in time, very roughly, we'll find that, where are we? there is, we find that we have this for the supply voltage. So this is Vs. So we can see the supply voltage is at an unusual, somewhere in the middle phase difference. And how we can work that out is by using these phasors here. And a phasor is, if you remember from simple harmonic motion, phasor is a rotating vector which will rotate, depending where it is, it rotates anti-clockwise, so remember that's always anti-clockwise rotation, and this would be VR. There's another one we're going to look at another time, and this is VC, lodged across the capacitor. Now, as this rotates, you can see that VR will, this one, as it rotates around this way, VR is going to hit a peak first, and VC is going to be over here at that point. And then when VR hits the next part around, when VR hits here, VC will peak. So that's 90 degrees behind. Now, when we're considering the two, let's just, sorry to use so many colours, but we'll make this our main one we're talking about now. This is VR, and this is VC, and the other ones we're ignoring for now. We'll deal with that in later videos. But if we're trying to find the supply voltage, we can just add these two phases as we would add vectors, top to tail, to find, that's a big arrow, we'll make that, to find the supply. So that would mean that the supply is on here, because you could transpose the VC over to here. So the supply voltage is the sum of the squares square rooted. So Vs is square root of VR squared plus VC squared. That's how we can work out the supply voltage. And remember, these rotating phases will actually give this sine curve up here if you look at them in detail. So lots of information there. Main ideas to take out of it is that capacitors lag behind. They take a while to respond or react, which is where that reactance comes from the previous video. The supply voltage at any point in time will still add up, will still be the sum of the VR and VC. But you can't use the RMS values to make a prediction about the supply voltage, because the supply voltage is an instantaneous thing, and that peaks in its own time as well. There we go.